All right, let's continue now with point charges. And this is starting at page 555. When you're dealing with a point charge, let's say it's at the origin, if we want to find the potential at some distance away from it, r, we usually use r just kind of for the circular symmetry of everything. The voltage, the potential at, voltage you usually think of as a difference. The potential at a point, a distance r away, is the electric constant, 9 times 10 to the ninth, times the charge, divided by that distance. And that's it. And we're going to choose v equals 0 at infinity. Just it drops off and further away. If you plug in an infinity into the kq over r, you get 0. And then if you have 2 point charges, the potential energy to bring them together, to set that up, is k q1, q2 over the distance between those 2 charges. All right, if you have more than one charge, you'll just have to add more and more potential energy terms. All right, and when we're talking about superposition here, instead of adding vectors where you have to worry about trig and finding the angles, Pythagorean theorem, you just add the values. No matter how many you have, you just keep adding them up. All right. Make sure when you're solving these problems, you make a diagram that shows all the charges, identify where it is you're trying to find either the potential or you're moving an object, convert everything to SI units, get rid of all the prefixes, make sure you calculate any unknown distances. Sometimes you'll have to use Pythagorean theorem to find some distance between 2 points. Find the potential for each charge separately. Plus or minus is important. Plus for positive charges, minus for negative charges. And then add all the numbers, so it should change to 6 every once in a while. These numbering things mess up. That's all right. So the potential at this point here, drawn in a diagram, label all the distances. The potential is just going to be kq1 over r1 plus kq2 over r2 plus kq3 over r3. Just add up those 3 potentials separately. All right, now last thing I want to talk about for this lecture is equipotentials. Equipotential is just basically 2 points that have an equal potential. You're moving along a specific path where there's no change. The change in voltage, the change in potential is 0. Q times 0 is just 0. So there's no work required to move it from one point to the other. So these are a few different examples of an equipotential surface. Now if you have the electric field pointing to the left like this, if I was moving up or down, it wouldn't change what that is. The distance moved in the electric field is going to be 0, so I could move it to the side and it wouldn't be affected by the electric field. Right? There wouldn't be a change. You wouldn't gain any energy moving along here. Right? It would be basically the same. Point charge, we could loop around in these circles. This point here is basically the same as this point over here. It doesn't matter which one we're at. One isn't kind of a higher level of energy. It's just moving along. Dipole gets a little bit trickier where you have a positive and a negative charge. It has a little bit uglier shape, but it's the same basic idea. And if you look at it, anytime we have these dashed lines, they're always going to cross perpendicular to the field lines, and you'll be able to see that in lab. All right, have a good weekend, and you can start on the ideas of capacitors before we meet again on Monday.